Well, hello. So yesterday, actually about 2 days ago, I was actually looking at reading an article about the New Horizons spacecraft, which is on its way to Pluto, and I was very interested in some of its onboard systems. I mean, not just its sensors, but also its propulsion systems. And apparently, it uses a pair, actually a set of monopropellant, I think, hydrazine thrusters. So of course, it's probably pressure-fed hydrazine that decomposes over a catalyst, and that provides thrust. But then, given the I actually conducted a review of research in solid propellants and certain additives that are used in solid propellants to improve their ISP. So, about how aluminum is added to solid propellants, but then because of two-phase losses, that gain is not really met. So essentially what I was thinking of, what if we can take what is the current research in solid propellants and basically, test them on small motors, which could be used as thrusters for spacecrafts and satellites, say for example the New Horizons spacecraft. So, I've read several articles actually about how there's research in using nano aluminum additives to basically enhance surface reactions, and that in turn would lead to lower two-phase losses. And of course there's research in using polymeric coatings to basically kind of create these small explosions at the burn-in surface. But either way, there's a lot of research in reducing two-phase losses. So, but all the papers I've seen so far, basically what they talk about is how you can, experimental results of these tests. They basically prepare different propellant batches, but then they never really presented results on, with actual motors in full-scale test scenarios. So I was thinking about, we can actually do a test on using some of these formulations they came up with. So it's not that hard to manufacture. There are some challenges there are some challenges in the manufacturing, but it is possible. They clearly detailed how to manufacture some of these products. And what I think we could do is, get some of those formulations and basically test them on actual propellant motors. But here's where I think we can have a marketable case. Think about producing these. Okay, so basically think of a crayon and think of that as a solid propellant. So basically you have a crayon, you have like a paper wrap around it. Imagine that as an insulation that basically encases the motor, and you attach like a small nozzle. These days with 3D printing or laser sintering, we can manufacture such casing, and then we make a formulation with some of these exotic propellants that they've come up with. But then we can actually test these. And now, if we were to use regular solid propellants, there'll be huge amounts of two-phase losses. And not just two-phase losses, there'll be straight-up incomplete combustion because of the short residence time. That's one of the big problems with composite propellant and solid motors. So, using some of these propellant batches, we could get test data on how much, what kind of specific impulses are we getting. But the reason I think this is really marketable is, monopropellant and hypergolic propellants do have a higher ISP compared to solid propellants, but then they have a much higher volumetric, they have a much lower propellant mass fraction, because you have to have all those systems to transport a liquid and everything. There's no liquid engine that can beat a solid motor in terms of propellant mass fraction. But then again, solid propellants have a higher density, so you would have a higher density ISP. So on some spacecrafts where space is a constraint, you can get a huge amount of delta V, I guess, per unit volume, if you think about it that way, for stored propellants. And these are extremely simple systems, as I said. So I was thinking of, think of a crayon basically with a small nozzle, maybe slightly bigger, and we could design some kind of a motor. But then I was thinking of using multiple of these, maybe even 50 of these or 70 of these, and you basically have a cartridge of these motors, and they can be, they can all be mounted onto a cartridge, and then you can ignite whichever one you want. So you basically have, you basically have like a thrust module that can be attached to the side of your spacecraft. And, so say on an interplanetary spacecraft, you want to have certain delta V's throughout its mission. You can basically ignite, several of these motors during your journey, wherever you want a certain delta V impulse to be. And now, solid motors, of course, can't be stopped, once started, and that is definitely one problem. So that's actually why I came up with the whole cartridge concept. And they have very, very high propellant mass fraction, so there's not much inert mass per motor. So once you ignite them, I know that there'll still be, of course, it's added weight, but it's very little added weight. So there's certainly a gain. There's certainly a business case here, and we could come up with very practical uses for some of these additives. So people have reported reduced agglomerate sizes. People have reported higher temperatures, but I've not found much data about actually testing these batches of propellants in actual motors. So I was thinking of us coming up with, we could do some testing. I actually came up with some 3D models, and I can send them to you. And yeah, it sounds really interesting. So you know what, we might be the ones to come up with these small cartridge-like motors that basically fire off several of them when, on a spacecraft when you want a certain delta V. So I'm going to send you some diagrams I made, some CAD models I made, and we might be onto something here.